Hello everyone, myself Varad. I am a doctoral student in the Department of Chemical Engineering, IIT Kanpur, and I welcome you all to this fifth lecture of thermodynamics. So in the last class, in lecture 4, we have seen about the definition of work, and also we have derived an expression for work done in a irreversible process. Further, we have also studied about what is the definition of irreversible work and what is a reversible work. So here, the work, if it is a continuous process, then the work done is called as reversible work, whereas if the work done is sudden, that is of an irreversible process, then the work is called as an irreversible work. So in today's class, that is in fifth lecture, we are going to derive an expression for reversible work calculation for an isothermal process. Further, we are also going to study about what is free expansion and work done in free expansion, and then further we also dive deeper into law of conservation of energy, that is the first law of thermodynamics, and derives some expression for work done for various other processes such as adiabatic process, isothermal process, so on. And let us start. So this is going to be fifth lecture, thermodynamics. So the first topic which we are going to see is, so in the previous class we have studied about reversible work. So let us write the definition of that thing again. A process or change is said to be reversible if it is brought out in such a way that the process could at any point or any moment be reversed by infinitesimal change. This is called as a reversible process, called as a reversible process. The second statement would be a reversible process proceeds. A reversible process proceeds. A reversible process proceeds infinitely slowly by a series of equilibrium states. Such that the system and the surroundings are always in near equilibrium with each other, right? And the processes which are not reversible are called irreversible process. So it may be noted that we can also relate work to internal pressure of the system under reversible conditions. It is to be noted that we can also relate work to the internal pressure of the system under reversible conditions. Volume changes from, let's say example, V1 to V2. It may be expressed as, in that case, W reversible is nothing but integral. Volume is going to change from V1 to V2, and this is going to be P external into change into volume, right? Hence we can write W reversible is nothing but minus integral V1 to V2 P external multiplied by dV, which means by W reversible is nothing but minus integral V1 to V2 P in plus minus dP dV, which is nothing but minus integral V1 to V2 P in dV, right? Plus minus, so this is going to be inside the integral, plus minus dP into dV. Now we know that both dP and dV are infinitesimally small, so that dP into dV is even smaller, is doubly infinitesimal, and hence can be neglected. Therefore we can write as W reversible is nothing but integral V1 to V2 P in into dV. Now for an ideal gas, we know that PV is nothing but nRT, which implies pressure is nothing but nRT by V. Therefore substituting this, from, let's say for example, call this as equation A, equation B, right? This is equation A and this is equation B. So from equation A and B we get W reversible is nothing but minus integral V1 to V2 P internal is nothing but nRT by V into dV, which what this implies W reversible is nothing but integral V1 to V2 for let us so nRT is going to be constant, nRT minus integral V1 to V2 dV by V, which implies W reversible is nothing but minus nRT into ln V, where V is going to change from V1 to V2. Accounting for the negative signs, this is going to be ln V1 by V2. So this is one of the expression which gives work done, right? So if you want to change this ln to log, this is going to be 2.30 T nRT ln V1 by V2 or minus 2.303 nRT ln V2 by V1, which is nothing but nRT minus ln V2 by V1, right? So these are all expressions which corresponds to a single V reversible. So hence what we can write is, at constant V temperature, what we have P1 V1 is nothing but P2 V2, right? Or V2 by V1 is nothing but P1 by V2. Therefore W reversible in that case is minus 2.303 nRT log of P1 by P2. So this is also one of the important expression. Now let us consider a case of free expansion. So in free expansion, what we have, let's say for example we have a container. Let us move on to the next. So free expansion, so for example consider a container, and let us consider gas is there, inside pressure is P internal and outside pressure is P external, right? And for example consider that P internal is greater than P external. Now if we do P external is equal to 0, then what is going to happen is, there is only one pressure which is going to, only one force which is going to apply in this case, and there is no opposing force, right? So then no opposing force, therefore work done is going to be 0, because there is no external pressure upon which gas has to work. So let us write this down. So free expansion, so expansion of a gas in vacuum, that is when P external is going to be 0, called as free expansion. It may be noted that no work is done during free expansion of an ideal gas, whether the process is reversible or irreversible, right? So this is a very important thing which we have to remember. In addition to these two modes, radiant energy and electrical energy are also modes of transfer of energy between the system and surrounding, right? So now let us look into very important aspect, which is units of heat and work. The heat exchanges are measured in calories. So let us write this down. The heat changes are measured calories, and the unit for that, abbreviation for that is cal. Kilocalorie, which is kcal. Joules, which is denoted as capital J, or kilojoules, right? And these are related as 1 calorie is going to be 4.184 joule, and 1 kilocalorie is going to be 4.184 kilojoule. The SI unit of heat is joule or kilojoules. Work is measured in terms of ergs or joules, right? And 1 joule is nothing but going to be 1 joule is 10 raised to power 7 ergs, right? And the SI unit of work, joule, right? And also additionally we have 1 joule is nothing but 1 Newton meter, which is nothing but 1 kg meter square second to the power minus 2. So how is that possible? We know that work is going to be nothing but force into distance, which is nothing but Newton into meter, which is Newton meter, which is nothing but 1 joule. Then force is going to be mass into acceleration, right? And then hence work is going to be nothing but mass, which is kg, multiplied by meter per second square, which is multiplied, right? So this is going to be force, right, multiplied by distance, which is m, which implies that work is going to be kg meter square by second square, which is nothing but kg meter to second minus 2. 1 joule is nothing but 1 kg meter square second to the power minus 2. The next topic which we are going to study is the law of conservation of energy, which is also known as the first law of thermodynamics. Law of conservation of energy, which is nothing but first law of thermodynamics. First law of thermodynamics. So the total energy of the universe is present either as a kinetic energy or as a potential energy. During a physical or chemical change, the energy may be converted from one form to another. Like for an example, when we throw a stone or a ball from, let's say for example, 5th floor of the building, so initially it has zero kinetic energy and a potential energy equal to mgh, and assuming that there is no air resistance, when we throw the ball continuously gains up energy in the form of kinetic energy and loses the potential energy, and as soon as it hits the surface of the earth, we say that it has zero potential energy and kinetic energy, which is going to be equal to its initial potential energy. Hence there is no loss of energy but only conversion from one form of the another. For like this we can also say similar things for the entire universe. So for example, the water stored in a dam possesses potential energy by virtue of its height. When the water is allowed to fall, its potential energy changes into kinetic energy. Due to its kinetic energy, the falling water can rotate the turbines and produces electricity. Thus, the potential energy of the water gets converted into kinetic energy. In other words, the total energy remains constant when the body changes its position, though one form of energy may be converted into another. This leads to an important conclusion known as the conservation of energy and has been put forth in the form of a law known as first law of thermodynamics, right? So what is the first law of thermodynamics? So let us write this down. So first law thermodynamics, right? It says that energy can neither be created nor destroyed, although it can be converted from one form into another. This law holds good in chemical reactions also, right? Energy may be absorbed or evolved in chemical reaction, but the total energy of the reacting system and the surrounding remains constant, right? So let us write this down as well. This is very important statement. This law holds good in chemical reactions also. Their energy may be absorbed or evolved in chemical reaction, but total energy of the reacting system and the surroundings remains. This law has been stated in several other ways, but the basic idea remains the same, that is conservation of energy, right? So we can write this as other statements of first law. So these are, for example, first one could be the total energy of the universe remains constant. The total energy of the universe remains constant. Number 2, the energy of the system that is isolated from its surrounding, that is isolated system, is constant, right? The energy of the system that is isolated from its surrounding, that is isolated system, is constant. So let us now study justification for the first law of thermodynamics. Let us move on to the next topic. Next page. Justification for the first law of thermodynamics. For the first law of thermodynamics, the first law of thermodynamics has no theoretical proof. It is a law based on human experience and has not yet been violated, right? This is very important. So there is no proof for this first law. The first law of thermodynamics has no theoretical proof. It is based on human experience and has not yet been violated, right? So it is based on human experience and has not yet been violated. It is right. The following observations justify the validity of this law, right? Let us write this down. The following observations justify the validity of this law. For example, for the first one is, it is not possible to construct a perpetual machine which can do work without expenditure of energy. If the law were true, it would have been possible to construct such a machine, right? So we will study what is a perpetual machine. So in short summary, perpetual machine is nothing but a machine in which total can be converted into work and total work input can be converted into heat, right? So we will study about it in our in subsequent classes. So for now, it is just suffice to note this down, note this statement down. So it is not possible to construct a perpetual machine which can do work without without the expenditure of energy, without the expenditure of, if the law were true, if the law were not true, then it would have been possible to construct such a machine. The second point is Jules in 1850 conducted a large number of experiments regarding the conversion of work into heat energy. He concluded that for every 4.183 joule of work done on the system, 1 calorie of heat is produced. He also pointed out that the same amount of work done always produces same amount of heat irrespective of how the work is done. James Joule in 1850 conducted a large number of experiments regarding the conversion of work into heat energy. He concluded for every 4.183 joule of work done on the system, 1 calorie of heat is produced. He also pointed out that the same amount of work done always produces same amount of heat irrespective of how the work is done. The third point is energy is conserved in chemical reactions also. For example, the electrical energy equivalent to 286.4 kilojoule per mole of energy is consumed when 1 mole of water decomposes into gaseous hydrogen and oxygen. On the other hand, the same amount of energy in the form of heat is liberated when 1 mole of liquid water is produced from gases, oxygen and hydrogen. These examples testify that the energy is always conserved, though it may change its form. So energy is conserved in chemical reactions also. For example, the electrical energy equivalent to 86.4 kilojoule per mole of energy is consumed when 1 mole of water decomposes into gaseous hydrogen and oxygen, right? On the other hand, the same amount of energy in the form of heat is liberated when 1 mole of liquid water is produced from gases, hydrogen and oxygen. So in a chemical reaction way, I can write water in liquid plus 286.4 kilojoule of energy gives me hydrogen in the form of gas plus half mole of O2 in the form of gas, right? So if I were to carry out opposite reaction in which 1 mole of hydrogen in gaseous phase reacts with half a mole of water, half mole of oxygen in gaseous phase gives rise to liquid water plus 286.4 kilojoule of energy. So these examples justify that energy is always conserved, though it may change its form. Right? First law of thermodynamics, right? So let us consider a general case in which a change of state is brought by doing work and by transfer of heat, right? So the internal energy of the system can be changed in two ways: by allowing the heat to flow into the system or out of the system, or by doing work on the system or by the system, right? So let us write this down. Let us consider a general case in which a change of state is brought. Is brought both by doing work and by transfer of heat. the internal energy of a system can be changed in two ways. First way is by allowing heat to flow into the system or out of the system. And the other one is by doing work on the system, by doing work on the system or by the system, right? So now let us consider a system whose internal energy is U1, right? So let us consider a system whose internal energy is U1, Now if the system absorbs Q amount of it, then the internal energy of the system increases. Then the internal energy of the system increases and becomes U1 plus Q, right? Now if work in amount of W is done on the system, then its internal energy further increases and becomes U2. Thus what we can write is U2 is nothing but U1 plus Q plus W. Therefore U2 minus U1 is Q plus W. Therefore we can write change in internal energy is nothing but Q plus W, right? So hence that is change in internal energy is nothing but heat added to the system plus work done on the system. The above expression is a mathematical statement for first law of thermodynamics. Now if a system does work in amount W on the surroundings, its internal energy decreases. In this case, work is taken as negative. That is W is nothing but minus W. Now if Q is the amount of heat added to the system, and W is the work done by the system, then in that case I can write delta is nothing but Q plus minus W, which is nothing but Q minus W. Therefore change in internal energy is nothing but heat added to the system minus work done by the system. The above relationship is between internal energy and work is also another mathematical statement for first law of thermodynamics, right? So in this class what we have studied? We have derived expression for work done for an isothermal process. Further, we have also seen that the work done is equal to 0 for a reversible, for a free expansion process. Further, we have also seen the units of heat and work, and additionally we have also seen the law of conservation of energy, which is nothing but first law of thermodynamics. We have given an statement for this, and then we have stated that there is no theoretical proof for this. However, there are certain cases, in almost all the cases, the first law of thermodynamics has been found to be accurate, and we have elaborated this with the help of a couple of examples, and then at the end we have given a mathematical expression for first law of thermodynamics. So in the next class we are going to study the work done for different types of processes, and then also we are going to study about the sign convention for heat and work for this first law of thermodynamics, and then if the time permits we'll also go into enthalpy change, which is nothing but another useful state function just like internal energy. So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.